Namaste. Welcome to this channel, Dr.ARM's Chemistry. We were discussing theories of acids and bases, in which we have seen several theories such as Levi's acid-base theory, Lorry-Bronsted concept, Arrhenius concept, etc. Then we have also seen the various aspects regarding the measurement of various properties of these acids and bases, that is such as the strength of the acids. Now we are discussing here acid-base strength, and in that we have to see this inductive effect. So this inductive effect is so this is inductive effect. It is also used to measure the strength of the acid. Means we can say whether the acid is stronger or weaker using this concept of inductive effect. So inductive effect is the effect developed by the attachment of the group or atom which is more or less electronegative to the any given atom, where there is replacement of hydrogen by this inserted group or atom. So as a result of this, we can see the change in the basic or acidic nature of the substance. So for this purpose, in order to understand, we will take some suitable simple examples. For example, if we take this PH3, and this phosphorus has a lone pair. So this phosphorus has this lone pair, and these are the pair of electrons which are used for bonding between phosphorus and hydrogen. Here, if we see that these hydrogens are replaced by same number of fluorine atoms, then we can get the different structure. So we can get this phosphorus is attached to fluorine, and with this electron pair. So here you will find that this is also a lone pair, and these three are bond pairs. So if we see the difference between these two, so according to this Levi's concept, these are carrying the lone pairs. So they are working as Levi's base. So we have seen two species, two compounds of phosphorus, where hydrogens are there, three hydrogens are there, and another where the three hydrogens are replaced by three fluorines. Now we have to see which one is stronger base and which one is a weaker base. Here the lone pair, according to Levi's base, the base is stronger, which is capable to share its lone pair more readily. So this electron pair releasing capability of the species makes it stronger or weaker. So this depends upon this bond pair, whether this bond pair is whether these bond pairs are helping this lone pair to get released, then it becomes stronger. So here, if we compare the electronegativity of the species, we find that hydrogens are much less electronegative compared to fluorine. So this bond pair is held strongly between the two atoms, but it is more here. If we compare the electronegativities of phosphorus and hydrogen, phosphorus is more electronegative. So these bond pairs are lying much closer to to this phosphorus. So electron density is concentrated on this phosphorus because of these hydrogens which are less electronegative. As a result of this, phosphorus is electron rich center, and this extra electron pair can be readily lost to the Lewis acid. In this case, if you compare that fluorines are electronegative elements and they have strong affinity towards electron. So these bond pairs are attracted towards these fluorines because fluorines are electronegative. As a result of this, electron density on phosphorus is reduced and it is moved on fluorines, and therefore this phosphorus becomes less electron rich or electron deficient, and this electron pair cannot be easily lost to the Lewis acid, and therefore this species becomes weak base. So this is weak base, and this becomes a strong base. So in this case, this bond pair is not withdrawing or not moving here towards hydrogens, but it is moving towards this phosphorus atoms. So we can show this movement like this, and because of which electron density is concentrated on phosphorus, and because of which this lone pair can be easily lost to Lewis acid. Therefore it is strong base. And here electron pairs are moving in opposite direction towards fluorine, and that is why phosphorus becomes a less electron rich, means electron deficient, and therefore it does not allow this lone pair to get discharged or donated to the Lewis acid. Here we will take another example. So if we take the example of ammonia, now you can see these ammonia, that is NH3. Then if we take another, means if we go on replacing hydrogens by R groups, that is methyl, ethyl, etc. So for instance, if we consider methyl group, then if we replace one hydrogen only out of these three by methyl group, then we get this MeNH2. Then again one more replacement of hydrogen by Me will give us NHMe2, and if all the three hydrogens are replaced, then we will get NMe3. Now here you will find that their hydrogens, nitrogen-hydrogen bonds, means there are lone pairs like this. These are lone pair on these species, and now the availability of this lone pair to be donated to the Lewis acid depends upon how this nitrogen becomes electron rich. So these hydrogens are much less electronegative, and therefore this electron pair can be donated to the Lewis acid. Compared to this, if we take this example, your hydrogens are like this, but there is Me methyl group or alkyl group. So compared to these hydrogens, methyl group is electron supplying group. Means if we show this like this, Me, then Me will supply electron density, means bond pair is moving towards nitrogen, as a result of which the electron donating ability of nitrogen increases. So compared to this, it becomes stronger Lewis base. So this is a weak base. This is a weak base, and this is relatively stronger base. Now again, if we see here, so this is the end. Then you will find that these two amine methyl groups are supplying electrons, but this is not supplying electrons. So electron density is increased on nitrogen, as a result of which this is again becoming stronger species, stronger Lewis base. And in this case, all these three are supplying electron density to nitrogen. So still the availability of electron pair for donation to Lewis acid increases strongly. So the strength of the Lewis base increases. So this is the strongest Lewis base. Strongest Lewis base. So in this way, we find that the electron donating inductive effect improves the basic nature of the basicity of the Lewis base. So inductive effect is nothing but the electron releasing effect or electron attracting effect, which creates strong impact on the central atom in order to make it a stronger or weaker base or weaker acid. Then if we take another examples. So now we have seen Lewis bases. Now we will see Lewis acids. So in case of Lewis acids, we will take the simple examples such as, say, BF3, BCl3, then BR3. Then we find that here we can show also this as so here we can show here the electron withdrawing effect is developed by these fluorines because these are strongest of all these halides. Then if we see this electron donating effect, you will find that this is again changeable. So if we are expecting that this fluorine BF3 is electron withdrawing effect, showing electron withdrawing effect. So boron is resulting a electron deficient species, and we are expecting that it should be a strong Lewis acid. But this is not so, because this fluorine and boron 2p orbital are showing back bonding. That is, they are showing pi bonds like this. So there is formation of this boron and fluorine and this 2p orbital. See why? and this fluorine lone pair. Fluorine lone pair. So they are showing back bonding. Because of this becomes weaker Lewis acid. So this is weak Lewis acid. Compared to this, boron trichloride becomes relatively stronger Lewis acid. So the strength of the Lewis acid is shown in this way. Again, BBr3 is still stronger, means strongest Lewis acid. So this is strongest strong Lewis acid. So in this way, the pi bonding effect here makes the BF3 a weaker acid, but we are contradictory expecting it should be a strong Lewis acid. But in this case, BBr3 is strongest Lewis acid. So with this, we will stop our discussion. See you next time. Please subscribe to this channel and press bell icon and like button. Thank you very much.